In this video, we shall refer to the absolute convergence test. This test can be applied to series with terms an of any signs. Instead of referring to the series itself, we take the absolute value of all the terms in this series and consider a new series instead. This test states that if this new series formed by taking the absolute value of all the terms an converges, then the original series, which is formed by having the terms an, also converges. Let's refer to the following example. We have the series which is formed by terms an equals to -1 to the power n divided by 2 to the power n. Instead of referring to this series directly, we consider another series which is formed by taking the absolute sign for all the terms an involved. So we get a new series. This is the same as considering the series with terms equals to 1/2 to the power n. Since for this series, it is a geometric series with the starting term a equals to 1/2 and the common ratio 1/2, since the absolute value of the common ratio 1/2 is less than 1, therefore this geometric series converges. And that is to say that this new series converges. Therefore, by the absolute convergence test, our original series, which is formed with terms equals to -1 to the power n over 2 to the power n, also converges. Please note the following remarks. We can see from the statements of the absolute conversion test, if the new series converges, then the original series converges. That is to say that to have the new series to be convergent, it is more strict than to have the original series to be convergent. In fact, there are series which converges itself, and at the same time, after taking the absolute value to each of the term an, a new series also converges. In this kind of situation, we say that the series converges absolutely. However, there are also other series which converges itself, but after taking the absolute value for each of the term an, the new series no longer converge. The new series diverges. In this case, we say that this original series converges conditionally. Therefore, you can refer to these two remarks here. We say that a series converges absolutely if and only if the new series, which is formed by taking absolute value of all the terms an, converges. And we say that the series converges conditionally if and only if this series converges itself, but the new series, which is formed by taking the absolute value of all terms an, diverges. In this example here, we see that this series itself converges, and the new series formed by taking the absolute value of each of the term an here also converges. Therefore, we say that this series converges absolutely. The following is a sketch of the reason why the absolute convergence test is valid. Please read it by yourself. Please make a pause here and try the following questions. We shall discuss the solution afterwards. Part A, we would like to determine whether this series is convergent or not. We consider taking the absolute value for all the terms an and consider this new series. And this series is actually the series containing terms 1/n to the power 5. We can see that this series is actually a p series of this form with p equals to 5, which is greater than 1. For p series, as long as p is greater than 1, then the P-series converges. Therefore, by the P-series test, this new series converges. And since this new series is actually formed by the original series by taking the absolute value to all of the terms an here, therefore, by the absolute convergence test, the original series also converges. In this case, since both the original series and the new series with absolute value of an converges, therefore we say that our series here converges absolutely. Part B, we would like to see whether this series converges or not. We can see that the numerator is cosine n. It takes a value between -1 to +1, whereas the denominator is n cubed. As n tends to infinity, the denominator tends to infinity. So we expect that the limits of an as n tends to infinity equals to 0. However, by the term test, we cannot conclude whether this series is convergent or not, and we need to use other tests to determine whether this series converges. Let us denote an to be cosine n over n cubed, and we denote bn to be 1 over n cubed. Instead of referring to this original series, let us consider a new series which is formed by taking the absolute value for all the terms an. That is the series which is formed with terms absolute value of cosine n over n cubed. These terms are all positive values, and then since cosine n takes values between -1 to +1, therefore the absolute value of cosine n takes the values from 0 to 1. Therefore, this term, which is the absolute value of an, is always less than or equals to bn, which is 1 over n cubed for all n. Now, if we consider the series formed with terms bn, this series is actually a p-series of this form, where p equals to 3, which is greater than 1. Therefore, by the p-series test, the series which is formed with terms bn converges. Now, we have the relations. The absolute value of an is greater than 0 and always less than or equal to bn, and the series formed with terms bn converges. Therefore, by the comparison test, the series which is formed by absolute value of an also converges. Now, since this is a series which is formed by taking the absolute value of the original term an and it converges, therefore, by the absolute convergence test, our original series, which is formed with terms cosine n over n cubed, also converges. In this example here, both the original series converges as well as the new series which is formed with taking absolute value to each of the terms an here also converges. We say that this original series converges absolutely.